All right, welcome back. Still using my headset because there's still a lot of noise in my neighborhood here. But let me know if there's any questions about what we talked about. Um, no, okay, I didn't see anything on the chat room, so I'm assuming that everybody's pretty much on board. So let's continue with our discussion here. Go back to our PowerPoint, and let's now discuss the Lewis structures of molecules. In other words, how do we use this concept, this symbology of dot structures to build the what molecules look like. We're going to do representations of molecules. All right. So pretty much all of you have done this in the past. You learn it either in your high school chemistry or your introductory chemistry class. And different professors have different methods for doing it. So what I'm going to do is I'm going to tell you why my method is. After that, you are welcome to use it or use other methods you prefer. I mean, as long as you get the final structures correctly, it doesn't matter how you got there. But I'm going to share with you the method that I use. So what I do is, first of all, I look at all the atoms in the molecule, and I count all the whole number of valence electrons. If what I'm drawing is, let's say, a polyatomic ion, then I have to either add or subtract electrons depending on what the total charge is. All right. Secondly, I'm going to draw a skeleton structure. In Lewis structures, you don't build from the left to the right, you build from the center out. Typically, the least electronegative atom is going to be in the center, with the exception of hydrogens, which are always going to be on the outside. All right. And then what I do is I connect all the atoms with single bonds in the most symmetric way possible. In other words, I connect them towards the center atom, not to each other on the outside. Step number 3, I look at all the electrons that I use to make the skeleton structure, and I subtract it from the total number that I started with. And I take those leftover electrons, and I'm going to add them back in, but there's a rule for this. I add them, first of all, as lone pairs, not one by one, but two by two. And I work my way from the outside in. So I start by adding lone pairs to the outside atoms until I complete octets in them, and then I proceed to the next one and then to the next one. Of course, the exception is hydrogen, because hydrogen cannot take more than 2 electrons, and if it's already bonded, that's the 2 electrons that it has in the single covalent bond. Finally, if after I have placed all of the available electrons, the central atom still remains without an octet, I cannot make electrons out of thin air. What I'm going to do is I'm going to switch or roll over lone pairs from the outside to form double or triple bonds with the inside or central atom until the octet rule is satisfied for all atoms. Okay, so those are the rules. That's the way I do it. I know other professors do it differently, but this is the way that I have. And so let's try a few exercises here for the remainder of this session. Let's do the newest structure for nitrogen trifluoride, NF3. And I'm going to go step by step. Number 1, count all the valence electrons in here. So nitrogen is group 5A, so it has 5. Fluorine has 7 because it's group 7A, remember? So that means that I have 1 nitrogen and 3 fluorines for a total of 26 valence electrons. That's what I'm starting with. Pretend that the nitrogen and the fluorines came in, and at the entrance to the ball, they check off their electrons into a box. And now I have a box with 26 electrons. It doesn't matter where they came from. All I know is I have 26 electrons. And when the nitrogen and the fluorines check out, all of those electrons need to be in there. Step number 2, I'm going to build a skeleton. In the periodic table, nitrogen is less electronegative than fluorine. So I'm going to put the nitrogen in the middle. And then I'm going to put the fluorines not in a row, but like a circle around it. And I'm going to connect them with single bonds. All right, so that's my startup. And now I'm going to put single lines between them. That's my start. That's my skeleton. Step number 3. Of the 26 valence electrons I started with, how many have I used already? Well, I had to calculate this. So I basically have, for every line, in other words, for every bond, that's one pair of electrons. And I have 3 of them. So that means 26 minus 6. I have 20 valence electrons remaining. So what I'm going to do now is I'm going to take those 20 leftover electrons and I'm going to put them as lone pairs to complete octets. But remember, you start from the outside and you don't go to the central atom until every outside atom has an octet. Okay, so let me start with the one on the left here. I'm going to put 3 pairs of electrons in there. And notice that between those 6 and the 2 that are in the covalent bond, that fluorine now has an octet. So we're done there. Let's say I go to the next one. Let's say with one in the bottom here. I'm going to put 6 electrons in there, or 3 pairs. With the covalent bond, and it's 2 electrons, that means an octet. So it's satisfied, no more. Now I'm going to go to the one on the right. I'm going to put 6 dots around it, or 3 pairs of dots, actually. Once more, between those 6 and the 2 that are being shared with nitrogen, I have an octet, and that's it. Now, remember, I had to add 20 more electrons. I've just added 6 on the left, 6 on the bottom, 6 on the right, so that's 18. That means that I still have 2 leftover electrons. Since all the outside atoms are now fulfilled for the octet rule, now and only now can I put that pair of electrons on the central nitrogen. Now, let's see if the central nitrogen is satisfied. Yep, it's got the lone pair, that's 2, and then 3 shared pairs, 6, so that's 8. Yes, it's an octet, and I believe all of them are placed in here. So let's do a quick check to make sure that all of the electrons in the structure are what they're supposed to be. So I have 3 single bonds, that's 2 electrons each, 10 lone pairs, right? 3 on the left hand fluorine, 3 on the bottom one, 3 on the right one, and 1 lone pair on the nitrogen. That's 10 times 2. So yes, 26 valence electrons. So remember that until you get kind of like a lot of practice in this, it's always good to do this check at the end here. Make sure that everybody's covered and that all the electrons are in the structure. All right, cool. Okay, let's try another one. Let's write the Lewis structure of the carbonate ion. I threw you a curveball here, right? I threw you a curveball. I put you with a polyatomic ion here. So be very careful, because in this particular case, when we count the valence electrons, carbon has 4, oxygen, group 6A, has 6, but there's a -2 charge, which means there are 2 extra electrons that I have to add in here, okay? Don't forget that. So I have 4 from carbon, 6 times 3 from the oxygen, and the 2 extra ones. So that's 24. Don't forget those 2 extra electrons. 24 total. Okay, now again, let's decide how we build this. Who is less electronegative, carbon or oxygen? Let's look at the periodic table. Now, typically, you can tell without the numbers based on their position, because between 2 atoms, the one that's farther to the left is going to be less electronegative. So carbon is less electronegative. So we're going to put it in the center. We're going to put the oxygens around, and we're going to connect them with single lines. Okay, so there's my carbon. I put the oxygens around. I didn't have to do it this way. I could have put them in I could have put the bottom oxygen on the top. It doesn't matter where I put them. I just did it this way because it was convenient and easy to draw. And now I'm going to connect them with single lines. That's my skeleton, quote unquote. Obviously not my skeleton, the skeleton of the carbonate ion. Okay, So now let's see how many electrons I used here. I made 3 single bonds. Each one corresponds to a pair of electrons. So that means that out of the 24 that I started with, I used 2 bonds times, 2 per bond times 3 bonds, 6. So that's 18 remaining electrons. And those are the ones that I had to put as lone pairs to complete octets. Okay? Okay, here's the tricky part again. Remember, you start from the outside atoms. You're going to add them 2 at a time. And until you complete an octet, you don't stop. Once you complete an octet, that atom is not going to get any more lone pairs. So let's go ahead and skip ahead and say we put these in there. So left-hand oxygen got 6, bottom oxygen got 6, right-hand oxygen got 6. I checked that they would be octets. So the one on the left, 6 plus the 2 that is sharing, that's an octet. One on the right, 6 plus the 1 that is sharing, that's an octet. One on the bottom, 6 plus the 2 that is sharing is an octet. What about the carbon? Oh, it needs 2. Let's put 2 more in there. Oh, guess what? There aren't any more. We've already used all 24 of the valence electrons that we had to start with. So we can't bring in extra electrons. Oh, but didn't we add a charge? Yeah. The 2 electrons that make the negative charge are already included in this package, right? Remember, we just put the electrons in a box. Doesn't matter where they came from. What matters is where we're going to put them in. So the rule is that since the carbon needs an octet and we don't have any more electrons, what we have to do is we have to basically shift. We have to roll over a pair of electrons from one of the oxygens into a double bond with the carbon. So let's say I pick that doublet there, that lone pair. In other words, what I'm going to take is I'm going to take that pair of electrons and I'm going to make that oxygen share them with the carbon so that I now have a double bond in there. See what I did? I couldn't add any more electrons, but I just basically rolled over a pair from the oxygen into that double bond. Now you might ask, well, did it have to be from that one? Could it have been from the oxygen on the left? Yes, it could have been. Yes, it could have been from the bottom one. I just picked that one because same thing, it was easier for me to draw it that way. All right. So essentially, the structure now has carbon with how many electrons around it? Now it has 4 bonds around it at 2 electrons each. That means it has an octet. So let's check. We have 2 single bonds at 2 electrons each, 1 double bond, that's 4 electrons, and we have 8 lone pairs, right? 3 on the left, 3 on the bottom, and only 2 on the right-hand oxygen. So this is just our bookkeeping to make sure that we have the correct number of electrons here. Okay? Give you a few seconds to double check, make sure you got the idea. All right. Now, the question that we asked was, did it have to come from that particular oxygen? And the answer is no. There was equal probability that the extra lone pair for making that double bond could have come from the oxygen on the left or on the right. And in each one of those cases, the double bond would be connecting the carbon to a different one oxygen. But we don't have a way really of pinpointing which one it is. Remember that in quantum models, there's a great level of uncertainty about things. So what we do is we draw what is called a resonance structure. It's essentially a kind of like a group of 2 or more Lewis structures to represent a single molecule that cannot be represented accurately by only one Lewis structure. So for example, we said that when we drew the carbonate ion, we had the structure we drew had, one of the oxygens forming the double bond with the carbon, right? But we could have done the one with the bottom oxygen. We could have done one with the one on the left, or the one that we did, which was the carbon oxygen on the right. And when I say right, I'm just talking in terms of the picture, right? Remember, if this is a molecule, it is turning around in three-dimensional space. So there really is no right or left. It's just basically, I'm just using that terminology to kind of refer to this particular way of drawing the pictures, right? Notice that I have all three of them kind of linked by a double-headed arrow. And what that represents is that these three structures are the three possible ways of connecting that double bond in this molecule. But the thing is that none of these structures exists by itself. What you have really is a blend of all three of them. So you can see the picture that I had there on the top there with the actual ball and stick model of the carbonate ion. You can see that's got like a triangle shape. And right now, the way it's drawn is the double bond is between the top oxygen and the carbon. But technically, every one of those oxygens has the same chance. And so it might be more accurate to simply draw it this way. Remember, this is not like structure on the left converts into the one on the right and it converts into the one in the center. No, this is not an interconversion. Neither of these three structures actually exists. They are a way of representing a structure that blends all three of them together, okay? So, but if you encounter a situation where you are asked to draw resonance structures, well, remember that resonance structures basically represent the same skeleton, but with different distributions of singles and double bonds connected by this double-headed arrow. Now, another question you might ask is, you put negative charges on the two oxygens of each representation here that are not double bound. In other words, the ones that have single bonds, they all have a negative charge in them. How did you come up with that? Funny you should ask. Let's see where that came from by doing a different type of structure. Okay, we're going to do another structure. We're going to do the compound called formaldehyde. Some of you have heard of this. It's a substance that is used to preserve biological specimens, right? Okay, same thing. Why don't you guys go ahead and add up the valence electrons. Carbon is 4, each hydrogen is 1, oxygen is 6, right? Okay, so you should have that total. Now, here's what happens. When I draw the skeletal structure, other than knowing that the carbon should be in the middle because it's the, the less electronegative one, and hydrogen can never be in the middle, I can come up with two possible skeletal structures. This one and this one. Notice the difference. In the one on the right, both hydrogens are connected to the carbon. The one on the left, one hydrogen is on the carbon, one hydrogen is on the oxygen. How do I decide which of those is the more accurate skeletal structure and gives me the correct Lewis structure? Okay, so the concept we're going to use here is essentially a mathematical calculation that's called a formal charge. Formal charge is when you look at an atom in the molecule and you calculate what is the difference between the number of valence electrons around an atom by itself versus the number of electrons that are assigned to it in a Lewis structure. So in a Lewis structure, since we're sharing electrons, we're going to pretend that each bond, which has a pair of electrons, one of those electrons is assigned to one atom and the other electron is assigned to the other atom. It's as if, although for the purpose of the octet rule, each atom counts both electrons, for the purpose of formal charge, you only count 1/2 of each bonded pair. So here's the formula. I'm going to look at every atom on the Lewis structure, And I'm going to find out, well, what is the total number of valence electrons that atom would have in its free state? In other words, the number I get from its position on the periodic table, minus all of the lone pairs or non-bonding electrons on that atom in particular. And then we're going to take 1/2 of the bonding electrons, okay? So if I have a structure, I count the number of valence electrons that element has. I subtract all of the lone or the non-bonding electrons that are on that atom, not the whole molecule, but just that one atom. And then 1/2 of the bonding electrons, again, because remember we said that each bonding pair, we're going to assign one electron to one of the atoms and the other electron to the other atom. Okay, so let's take these proposals for here. One more rule before we go on. If you calculate formal charges, when you add all the formal charges of all the atoms in the molecule, it must equal the charge on the molecular ion. Obviously, if it's a molecule, it should be 0 charge. So if you add up the formal charges, they need to add up to 0. All right, that's very important. Great. So what I'm going to do now is let me take the skeletal structure there on the left, the HCOH, and let me complete the Lewis structure based on that skeleton. There it is. Now, the first thing is, let's make sure that on the basis of criteria, this works. First of all, I should have had 4 electrons from carbon, 6 from oxygen, 2 from hydrogens for a total of 12. And in this structure, I have 2 single bonds, that's 4 electrons, 1 double bond, that's 4, and 2 lone pairs, that's 4, so that's 12. Okay, so as far as conservation of mass is concerned, this structure obeys the rule. All the electrons are there. Now let's check the octet rule. Oops, I forgot to do that. Anyway, hold on a second. Before we go here, let's make sure that this obeys the octet rule, correct? All right, so we look at carbon, and there are 2 electrons and then 3 bonds, which would be 6, that's 8, so that works. Let's look at the oxygen. Same thing, we have the single bond, the double bond, so that's 1, 2, 3 bonds at 2 electrons each, that's 6, and the lone pair, that's 8. So as far as the octet rule is concerned, this structure works. So let's apply now the formal charge criterion. And we're going to apply it simply just to the carbon and the oxygen, because the hydrogen, you know, it's on the outside. That's it. That's the only place it can be. So what would be the formal charge on the carbon? Okay, the valence for carbon, we said from the periodic table, is 4, right? Now we're going to subtract the non-bonding electrons on the carbon. There's 2. Notice it's not on the whole molecule, just on the carbon. And let's see how many electrons are involved in bonding here. So we have a single bond there and a double bond there. So that is 2 plus 4, that's 6. So I'm going to take out of the 6 bonding electrons, 1/2 of them as belonging, quote unquote, to the carbon. And that means that the carbon now has a formal charge of -1, and I'm going to write it up there. Give you a few seconds in case you have any questions about how I arrived at those numbers. Okay, let's try the oxygen now. The valence of oxygen is 6, right? Now, in this structure, oxygen has 2 electrons that are not part of bonds. So I'm going to take 6 minus 2. And oxygen also has a double and a I apologize for that interruption. I believe that we were doing this, and hopefully the video works here. So this is kind of like a re-recording of this part of the lecture because apparently when we did it live, it didn't record. So I'm picking it up. I think this is where we got interrupted. So we were discussing formal charges, and our next one is going to be the formal charge on the oxygen, right? And we're going to say that oxygen has a valence of 6. And in this structure, there is a lone pair. So that's 2 non-bonding electrons. We subtract that. And then in this structure, there are a double and a triple bond. So that's 6 total electrons. And we're going to count half of those as part of the oxygen to give us a formal charge of +1. And we can write that up there. Okay, so in this structure, the carbon has a -1 formal charge. The oxygen has a +1 formal charge. Okay, let's look at the other structure. So if we had finished the structure using the other skeleton that we proposed, this is the structure we end up with. Once more, let's make sure that all the criteria are met. Number 1, are we using all 12 of the electrons that we started with here? Okay, so we have 2 single bonds, 1 double bond, that's 4 more, 2 lone pairs, that's 4, so that's 12. So at least we know that criterion is followed, is obeyed, and we should be okay with that. Now let's look at the criterion of octets. Does every atom here obey the octet rule? Now the hydrogens, we don't count them because they're on the outside, but you can see where the oxygen here has 2 lone pairs and then 2 bonded pairs for a total of 8. So it satisfies the octet rule. And let's look at the carbon now. So you can see how the carbon similarly has all 4 sets of bonded pairs here. So that'd be 8. So in other words, the carbon is obeying the octet rule. So we're going to take that out of the way and continue our discussion. So let's going to apply now the formal charge criterion to this structure. Let's start with carbon. Again, valence of carbon is 4. In this particular structure, the carbon has no lone pairs on it. There are no non-bonding electrons, so we subtract 0 for that. And we see that in this structure, carbon has a total of 4 bonds, like 2 singles and a double. So that's 8 electrons total. And we're going to take 1/2 of those as if they were assigned to the carbon. And you can see this generates mathematically a formal charge of 0 for the carbon. Let's look at the oxygen now. Again, valence of oxygen is 6. In this structure, the oxygen has 2 lone pairs, so that's 4 non-bonding electrons we're going to subtract. And then it has a double bond, which means there are 4 bonding electrons, half of which we're going to take to assign to the oxygen. And so we have a formal charge of 0 here. Now, again, when we look at these criteria, and particularly this formal charge criterion, the emphasis is on the word formal, all right? We are not saying that if an atom has a formal charge in a molecule, that it has that as an ionic charge. It's not ionic. It's a formal calculation. It's a mathematical assignment that says, you know, in that particular environment, that particular atom is feeling that its electron surroundings are different than they would be if the atom were by itself. That's all we're saying. In some cases, yes, there will be an actual negative charge if we're talking about an ion, but in many of these, for example, this molecule of formaldehyde, which is neutral, there is no such thing as the carbon or oxygen having a charge, okay? Again, emphasis is on the word formal, and it is a purely mathematical calculation. Now, we did the calculation for both molecules. Now let's see how we use that, all right? And actually, this is what this molecule would look like if we did the Wallenstein model. Number 1, for neutral molecules, a Lewis structure in which there are no formal charges is preferable to one in which formal charges are present, all right? So if I have two structures and one of them shows me, a formal charge of +1 here, a -1 over there, and I have an alternative that doesn't show any formal charges, the one with no formal charges is preferable. Now, let's say that we do have to have formal charges. There's no alternatives with no formal charges. In that case, the structure with large formal charges is less plausible than one with small formal charges. So if one structure has a formal charge of +2 in one atom, -2 in another atom, and the other candidate has +1 and -1 respectively, the second structure is more likely to be correct because it has smaller formal charges. Now, let's say that, again, you have the formal charges and you already know you can't get away from it. The most plausible structure for these kinds of situations is one in which negative formal charges are placed on the more electronegative atoms. Let's say you have a structure that has a formal charge of -1 on a nitrogen and +1 on an oxygen. And then you have another one that puts a +1 formal charge on the nitrogen and a -1 on the oxygen. Notice that they both add up to 0, so it's okay. However, the second structure places the negative formal charge on oxygen, which is a more electronegative atom. And therefore, that structure is more likely to be correct, okay? So with these criteria in mind, let's ask again, which is the more likely Lewis structure for formaldehyde, CH2O? This is the first candidate we discussed, and this was the second candidate. If you think about it, looking at criterion number 1 here, you can see that a Lewis structure in which there are no formal charges is preferable to one in which formal charges are present, all right? So you look at these two, and yes, I think the answer should be obvious. The candidate on the right is the more likely because it doesn't force any formal charges on any of the atoms in here, all right? So that's what we got. Okay, now what we're going to do is over the next week, you're going to be receiving an opportunity. It's going to be like a lab guided activity where you're going to be given a table of formulas and you have to write the Lewis structures. I'm going to wait a little bit before I post that because I want you guys to focus right now on that spectroscopy activity with the LabFlow platform. And so, it'll be there, but don't worry, once you get it, usually if we do this in class, it takes us about half an hour to do it. They're fairly easy to do. But here we go. That's what you're going to get. Now, when you start practicing these things, there are certain things you notice, and you can come up with some very quick tricks or kind of like rules of thumb. For example, carbon generally has 4 covalent bonds. So the majority of molecules that have carbon in them, there are going to be 4 lines coming out of the carbon. I mean, it could be 4 single bonds. It could be 2 double bonds. It could be a double bond and 2 single bonds. It could be a triple bond and a single bond. Whatever combination you have of 4 lines coming out of carbon, that's typically what's going to happen. Nitrogen generally has 3 covalent bonds coming out of it. Every now and then it'll have 4, even though it'll put a formal charge on the nitrogen, but it happens. Oxygen, you'll typically see either 1 or 2 lines coming out of it. So, that could be a single bond or 2 single bonds or a double bond. Typically, those are the scenarios for oxygen. Now, halogens, right? The fluorine, chlorine, bromine, those kind of guys. These atoms, when they are on the outer boundary of the atom, when they're not a central atom, they're typically going to have only 1 covalent bond and then a bunch of lone pairs or non-bonding electrons, all right? Now, be aware that for big atoms like chlorine and bromine and iodine, one of the things they can do is they can make compounds that essentially don't follow the octet rule. They can expand beyond the octet, and so they can act as central atoms. Fluorine doesn't do it, but chlorine, bromine, iodine, those guys can do it. And in those cases, yes, there'll be more than 1 bond. And don't forget that hydrogen can only form one covalent bond. That's why hydrogen is always on the periphery, always on the outside of these atoms. So whenever you end up with a structure that results in bonding patterns that are different from these little rules here that are common, what that means typically is you're going to have formal charges in those atoms, okay? So let me close out by showing you this little exercise. I'm going to let you guys do this at home. What is the probable Lewis structure for a molecule with one atom each of carbon, nitrogen, and hydrogen, okay? So just for the sake of it, rather than Google it and look it up, just go ahead and write out the possible skeletons in here that you could have, and then the different bonding schemes, and then apply the formal charge criterion to choose the one that is correct, okay? It'll be a better practice for you, all right?